This is the hour where we go into electrical performance and signal and power integrity. Because specifically, I need to tell you some of the problems in high-speed design and signal and power integrity that HDI makes it simpler. It kind of solves them. It also might explain to you questions you might have about, will this work electrically? I should bring up that the very first HDI board that I ever built in 1982 was because we had just perfected a 32-bit microprocessor. So it was a 32-bit computer and a piece of silicon. Later, it would be licensed by Intel and be called a Pentium. But Intel did not develop the Pentium. Hewlett-Packard did, and we licensed it to Intel. And 6 years later, Intel, quote, invents the microprocessor, 32-bit microprocessor, which is okay, because HP is not going to sell the chips. And we didn't mind them taking credit for inventing it, even though they licensed it from us. But so the technology was NMOS3. Any of you kind of familiar with semiconductor technology? I started in integrated circuits. I didn't start in printed circuits. I started in integrated circuits. But because I'm a chemical engineer, Hewlett-Packard asked me if I would go down the hill and help the people making printed circuit boards. And my thing was, well, what's a printed circuit board? kind of thing. And so I'm in Palo Alto, California, Page Mill Hill, and I walk down the hill to Porter Drive where they make printed circuit boards. And I walk in this building, and I see all these mechanical drills and these bubbling acid tanks filled with stuff. And, you know, and everything in semiconductor is very clean and pristine. And I was kind of walking this thing with our acids everywhere and bubbling liquids and smells and ammoniacal etchants. And the etchant they were using was chrome sulfuric, hexavalent chrome in sulfuric acid. And I'm asking, who's the safety engineer here? This is a disaster waiting to happen. And they pointed out to a tank to me for a thing called tin nickel, and the pH was adjusted with hydrofluoric acid. Any of you kind of understand the significance of hydrofluoric acid? Well, nobody raising their hand. Hydrofluoric acid is a really bad thing. It will burn through your skin and dissolve your bones. It is a nasty, nasty, nasty thing. And I'm saying, you're adjusting the pH of this thing with hydrofluoric acid? Where is the neutralization salve? And they said, what? I said, this thing will kill you unless you put on the antidote within a few minutes. Where's the antidote? What are you talking about? And so I'm just saying, who's the safety engineer here? We don't have a safety engineer. I said, well, don't let the Environmental Protection Agency in here, because you know you just shouldn't be doing this. But anyway, they had technical problems, and I don't know anything about printed circuits, but I know how to solve problems. And methodically, I went through and fixed all of the problems. And the result was, this guy must be a genius. No, I'm not a genius. I know how to solve a problem. And it doesn't matter to me. My advanced degrees are in semiconductor in process control. And in process control, I treat things as a black box, looking at input and output and the transfer function. So every printed circuit manufacturing problem, to me, was just another black box. And so I had a methodology to solve it. Unfortunately, the electrical and mechanical engineers had no training in this area. And to them, they were doing it wrong. They were holding everything constant and changing one variable at a time. Unfortunately, the solutions turned out to be multiple variables interacting, and 2/3 of those variables were qualitative, not quantitative. And as engineers, they went after the quantitative variables and they ignored the qualitative variables. Qualitative variables would be day shift versus night shift, vendor A versus vendor B, tank number 1 versus tank number 3, drill number 7 versus drill number 9, spring versus fall, because the water changed. They didn't realize that the water changed between spring and fall, and that changed the reaction to the chemistry. I didn't know either, but setting up the experimentation, it pointed out that this is the cause, or these interactions are the cause, so I knew how to solve it. It wasn't that I was a genius. I'd been trained at the university how to solve a problem. In chemical manufacturing, I was a chemical engineer. And my professor once told me that we hardly deserve the title of engineer, because in chemical engineering, we do some pretty crude things that engineers, and that we cannot consider ourselves exact, because some of the best models I worked with had 300% air. But a mechanical and electrical engineer worked with 1%, 5% precision. Well, not in my business. In my business, I work with 300% air, and I'm not alarmed by that. The whole point is, how do you manage that area of uncertainty? And I was trained to do that. And so it was so much fun that I did not go back to semiconductor. I stayed with printed circuits because I thought, you know, there's an endless number of problems, and this is going to be fun. And it was. For the next 30 years, it turned out to be a great area. But I do have a degree in electrical engineering. And so, but my focus is really control theory, and control theory for chemical, not control theory for mechanical dynamic kind of this. It's control theory of interacting chemicals, which involves chemical kinetics. And chemical kinetics is really quite dynamic in terms of control theory. So it was just luck, you might say, that put me there for that problem. And so this kind of, I don't know how much I have an awareness of new materials, but if you're involved in HDI, you should probably already know that we have a special subset of materials just for HDI that are not used in multilayers. So if you've never heard of that, better spend some time reading up on it, because there's a whole series of materials that are cheaper and higher performance for HDI that you cannot use in a multilayer, because they are only for the laser drilled thin layers. And so material advantage. And then we'll talk about signal integrity and power integrity with HDI. So one of the problems, like I mentioned to you before, is like this Intel device. This is a 280 watt that draws 200 amps in its turbo mode. You can tell this dude gets hot because there's a cooling tower just for the processor. So this is a workstation. This is obviously not a notebook computer, not with that cooling tower right there. And drawing 200 amps is a little too much for a notebook. But your higher performance workstations, and believe me, the new generation of workstations from AMD and Intel have 24 threads to 32 separate threads running in them. They are they're a supercomputer, but you have to plug them in the wall. They just draw so much current that it's not practical to use them with batteries. And they have to have these big cooling towers, liquid-cooled, closed-loop cooling systems to keep the heat under. This thing has a 3.2 gigahertz clock. It has 3 memory channels. These were DDR3 at 1.6 gigahertz, but only 1.4 volts. So one of the problems with using this guy is you're designing the power distribution network. If you're looking at the impedance of the power distribution, it's kind of equal to what ripple can you afford times the voltage divided by the current max. Well, if you look down there with the quad core, if you're drawing 200 amps and 1.4 volts, and you only want a 1% ripple, then your power distribution network has to have an impedance of 0.007 ohms. That's that's nearly zero. And you can't get to zero, but 0.1 and 0.01 are typical goals now that your power distribution network gets. Well, I'll show you later. You're only going to get that unless you use very, very thin dielectrics between your power and ground layer. That is the only way you're going to get that low in impedance. And so I'll show you later. But that's modern chips. The chips are, when you got 2 billion transistors, the thing gets really hot and uses a lot of current, even though the voltage is low, which means you've got a reduced noise budget, but it's not for the faint of heart. It's tough design, but it's worth a lot of money, whoever can design with these chips for products that they use. And so one of my personal friends is Dr. Eric Bogentin. I've worked with Dr. Bogentin. I was at Hewlett-Packard, and he was across the street at Silicon Graphics. And so we're all in Silicon Valley, and we all know each other from different things. And since Dr. Bogentin was really the foremost expert in signal integrity, at meetings and things like that, we had a thing called the California Circuits Association that we would meet each month. You know, I would ask Dr. Bogentin the questions about impedance and signal and things like that. And he has very good at explaining very complex. In fact, I have a lot of his books that I was able to download when he gave them away for free. Now you have to pay a lot of money for his books. But I've got all the stuff before he charged for them, a lot of his material. And one of the things that he gave me was the signal integrity noise came in 4 families. And the first one was the signal quality from one net due to reflections and distortions within one net. The second one is crosstalk between multiple nets with ideal return path with or without simultaneous switching kind of things. Number 3, the noise caused by the rail collapse of power ground distribution network. And the fourth one, external noise, EMI, from components of radiation. And so to me, noise can be a very complicated issue, but reducing it to this 4 families, so if you look at what are the sources of noise, here's a whole list of where noise comes from. So if you read down the list, you realize, oh, those are some best practices. Those are rules that I've been learning and people have taught me. Yes, they are. These are things. But, you know, like power rail collapse. But, you know, down here, excessive stubs, branches, and bifurcated traces. Improper impedance matching and termination. But anyway, there's my favorite, cutouts in power or ground plane. You all know that, you know, you don't put a cutout in a power or ground plane if it interferes with the return path of your signal, because then the signal, the return path is going to have to go around it, and you've induced noise and things like that. But, well, so Dr. Boken and I got into how does HDI, the HDI features, help solve some of these problems. So here are the HDI features, and on the left-hand side up there is, does it improve signal quality? Does it improve crosstalk? Does it improve switching noise? Or does it improve and lower EMI? And so some of the inherent advantages of HDI that you should be designing with, since you chose to use HDI, is like this, is shorter interconnect length. You should move your parts closer together and shorten the time of flight, the interconnect length. The thinnest dielectric materials between power and ground and for laser drift are low dielectric constant materials. So you should be using not FR4, but low dielectric unreinforced materials, not FR4. Let me tell that again. If you're going to do HDI, you should not be using FR4 for the HDI layers. For the core, you can use FR4. If you're using any kind of glass woven FR4, you are spending extra money and not getting better performance. If you've never heard of these new materials, then there's some education you need to learn about new materials just for HDI, not for multi-layers, just for HDI. The VIA pad. Why the VIA pad? Because VIAs are the biggest source of inductance. And the pad is an appendage you don't want because the pad makes it into an antenna to transmit noise to other parts of your circuit. And so fine lines and thin dielectrics, that goes with the low dielectric constant. And the last one is power coupled to ground. In other words, moving that power and ground plane to as close as possible to get those materials. Those are kind of all characteristics of higher performance HDI that should be showing up in your designs. This one is particularly interesting because the biggest culprit and the worst thing you can possibly do is use a through hole. The through hole, although it's essential, is the worst construction possible because you can see up there that that through hole, even though it's not electrically connected, it capacitive couples to every single layer that's close to it. And so if there's noise on your power, it will go into that hole. Once it's in the hole, the noise can be sent to another net signal line. And so you must get rid of these big holes because they take up a lot of space, they fail early, and they distribute noise all over the place. And you don't want noise being distributed. What you want is something that looks like this, and you want to minimize that guy in that way and use more of those if possible. For one thing, it looks like this. If you can isolate the most sensitive nets in a pure HDI layer and then throw in a ground plane and keep it separate from the rest of the nets and nowhere near any through holes, then there's no way that the noisier part could, through the through holes, can get up into your more sensitive nets. And so what we're really talking about now is a true three-dimensional construction of what you're trying to design. It's not really two-dimensional anymore. This is getting into three-dimensional things. And almost none of the design tools do three-dimensional signal integrity. They still kind of give you an X and Y two-dimensional. But you got to remember, your multi-layer HDI board is a three-dimensional product, and it's got holes running through it that makes it very kind of complex all the way through. And so one of the problems with through holes is via hole inductance. So back to my first thing. The very first HDI board that we did was we had invented this 32-bit microprocessor. They put it on a standard multi-layer everything, and they fired it up and it wouldn't work. And, you know, they were spending hundreds of millions of dollars to invent a semiconductor, and it wouldn't work. And as they are testing it, it wouldn't work for two very important reasons. It didn't have enough energy to drive FR4. Number two, it was the inductance of a VIA, a 1.6 millimeter thick PC board, had too much inductance for the NMOS3 to drive. So the physicists, they started back calculating, and they came to us and they said, to make this chip work, we need a PC board that's made out of pure Teflon. Okay? So we want an 8-layer pure Teflon multi-layer. And they said the vias could only be 1.25 millimeter, can only be 125 micron diameter and 125 micron deep. Now, this is 1982, and they're telling us that they have to have a PC board that looks like this. And we're kind of scratching our head because no PC boards look like that. Nobody makes an 8-layer pure Teflon with little tiny stubby vias. For one thing, but we had to do that. We got hundreds of millions of dollars on this chip. This chip needs this kind of PC board for electrical performance, not for density. So, okay, so down the street is coherent radiation. We walked down the street. We asked coherent radiation, can we build a laser drill? They said, sure. You buy this laser, you put it on this XY table. So we built a laser drill so that we could make very tiny holes in Teflon. And then we found out that electroless copper won't stick to Teflon. So I'm semiconductor, and I said, wait a minute. I said, we can plasma etch this thing to make anything stick to it. And if it doesn't stick to it, we'll use a titanium sputtering, and the copper will stick to the titanium. Okay, so we got a way to metalize this thing. And then we figured out how do you plate it, and on and on and on. But so we made them. Oh, and the NMOS 3 was a couple hundred watts, so it had the heat dissipation of a nuclear reactor. So okay, we'll make the center of the multi-layer a solid copper plane, and we'll mill down so that the chip can be mounted on this copper plane in the center to cool it. Then you wire bond up to the pure gold plating using the Teflon dialect, And so I was talking with the Altium folks. Should I bring those boards here to let you pass around? They said no because students don't like to hear about stuff 30 or 40 years ago. So okay, you wouldn't be interested. I said, by the way, if I pass this board around, nobody today in Germany can build this, or in the US or anywhere. The technology exceeds what anybody can do. And we were making this in a high volume in 1985. So I like to show fabricators because what we were doing in 1985, they can't even do today. They ain't got the slightest clue how to do that today. For one thing, nobody knows how to metalize Teflon. You have to use a thermoset, metalizing pure PTFE. But our job was to make multi-layers for 100 gigahertz RF analyzers for HP test equipment. We knew a lot about using thermoplastics in RF environments that nobody in the world still doesn't know about, that we perfected to make. Because the HP test gear has to be 10 times better than what it's measuring. So what it's measuring is what you're designing. But our designs have to be 10 times better to make it an accurate test equipment. I've worked with 300 gigahertz circuit boards and test gears. 30, 40 years ago, we were at 300 gigahertz. When we switched to optical, I've made optical PC boards that don't use electrons, they use photons. I'll show you that, the last thing. I've worked into the near 1,000 gigahertz area that's optical. And I've done it for 20, 30 years because you had to make optical test equipment for optical circuitry. That's why a career at Hewlett-Packard was really, really fun. Just endless challenges every day to how to do something better or test it better. So this one right here, notice that the axis is the length of a via. I apologize that it's 10 inches. And the vertical axis is nanohenries. And depending on the diameter and the length, the inductance always goes up. And so vias are bad, because vias are our main source of inductance. The trace inductance is pretty low, but via inductance is enormously high. Well, this is what happened in 1982. This semiconductor could not drive the 15 nanohenries, which was the inductance of the via in the FR4 board. It could also didn't have the energy to drive the dielectric constant of FR4, which is 0.02. It needed a material that was 0.0004. The only material that's 0.0004 is pure Teflon, PTFE. Not ceramic Teflon like the RF guys sell, pure Teflon from DuPont. So we made them multi-layers that electrically matched what the semiconductors. So the first HDI board was not density driven. It was based on electrical performance simply the thing. Later on, fine pitch became the driver and miniaturization became the driver, but that's not why we invented HDI in '82, was electrical performance. And now that we're going to 5G, we've come full circle that we already now understand the electrical performance advantages and how to use them more swiftly. The whole thing about stubless nets, is that these high frequency go out, they hit a stub, they'll reflect back and distort the waveform. And so what do people do in the telecom? They use through holes and then they pay extra money to have them back drilled. In other words, to drill out the stub. Whereas with HDI, we can create a construction in which the via starts where the signal comes in and the via ends when the signal goes out. They're stubless. So HDI technology provides 100% stubless routing. And the next talk, I'll go into the architectures of how that's done. We're still talking about first generation HDI that's 40 years old. In the next hour, I will talk about 20-year-old HDI technology and 10-year-old HDI technology, which you don't do here in Europe. But if you want to kind of get ahead of the competitor, instead of implementing the 40-year-old stuff, I recommend you implement the 10-year-old technology, not the 40-year-old technology. But you have to be aware that since this technology is 40 years old, we've gone to second generation and now third generation. And the iPhone uses, and the Samsung use third generation, not first generation. If you've ever taken an iPhone apart or looked at a breakdown. Well, and you saw the thing about noise from stubs and as a function of frequency and thickness of the PC board. And here's an important one. Via capacitance versus via planes. Why do I constantly emphasize how to do it with half the number of signal layers? The reason is, every time you add another plane of copper to any multi-layer, all of the vias degrade. All of it. So every time you add a layer, you're killing your electrical performance. So when people say, I can do this with 36 layers, I say, fine, if you want to drive yourself into bankruptcy, learn how to do it in 18 layers or 12 layers. Do not be proud of using 36 layers. That just indicates that you don't know what the hell you're doing. Because look at that graph. Every time you add a copper layer, all the vias go up in inductance and capacitance. It's a cumulative effect. So thinner is better. Fewer layers are always better. They cost less, they're more reliable, but electrically they operate better. That's not me, that's physics. It's just pure physics. That every time you add a copper layer, you're killing all the electrical performance for all the nets, kind of thing. And the problem is that I have not seen these graphs in any electrical book or design book. The only place they exist is the ones that I've created, but I've created them working with the scientists at the labs or with Eric Bogatin. So it's not secret. It's just that nobody ever asked the question or something, I guess. And this is an important one here. And interesting enough, this one is in German. So I didn't create this one, and frankly, I don't know who in German, but this is a high-speed electrical net, and it has 3 vias. And on the right-hand side, the vias are through-hole, but on the left-hand side, the vias are micro-vias. And look at the signal response of a high-speed pulse going down that net when it hits the vias. you can see very clearly that each through hole has a profound effect. The inductance of that through hole is a profound effect of the signal response, whereas the microvia is virtually invisible. Well, in 5G, that's really, really important, that you have to be so cautious about the vias you use because the nets you're working with are such high speed that it's all RF radio kind of work that you're working with, even though you're in the digital mode. Another set of EMI, this is the through hole board. This is the board where I moved ground plane to the surface. So this one, I have a Faraday cage. Well, which one passes the EMI testing? Not the one with all the emissions. It's the one where I move the ground plane to the surface, because I got a Faraday cage that bottles them up. And everybody is fighting EMI problems. Why? Because you got your damn ground plane on layer 2, and you've got your signals on layer 1. So, and in many times, you've actually got antennas all over the board, and you wonder why you don't pass EMI. Get that ground plane up to the surface and get your signals down under the ground planes in the center of the board, and you'll start to get EMI under control. Because without it, and so what I see some people doing is they're screening a silver paste on top of the solder mask to create a Faraday-like cage, which just costs more money, but you could design that in to begin with. When I get to the case study, I'll show how you're all flying on a lot of my designs, because on the 787, Boeing chose to use optical networks. There are no copper wires in the Boeing 787. It weighs too much. Plus, it's a plastic airplane. It's not a metal airplane, it's a plastic airplane. All of the control wiring is optical, and it's in fact a triple redundant optical network. And I was involved in how to design the HDI boards for the optical networks, because these are extremely high frequency, going from digital to optical and back to digital. And one of the things we did is by moving the ground planes to the surface, we lowered the EMI so that we threw away the metal card cage and lightweight plastic. Well, Boeing gave $5 million bonus to every kilo that you saved on weight. And we saved several kilos, and so the group I was consulting for collected the $10 million bonus from Boeing, because every single PC board was so quiet, it didn't need a metal card cage as a saved a lot of weight on that particular airplane. But we'll do that later this afternoon. So here's your power supply impedance, and the colored lines up there are different kinds of decoupling capacitors, including the multi-layer, multiple element decoupling capacitor that are the lowest inductance you can buy. That's the blue line. But the only way to get to the black line up there is to have power and ground very close together, because that's a spreading capacitance, not an individual capacitor. And it works because the impedance, inductance is nearly zero. I'll show you that in a little while. So the only reason that works is all the other chip capacitors that are components have too much serial inductance. There's just no way to get around that inductance of components. But inductance is the problem that we have. And so only HDI can solve many of these inductance problems. It cannot be solved with a conventional multilayer. And so you kind of see that, so what we do is we have ground on the surface and we put power as close as we can possibly get it. When I mean close, I'm talking about 13 microns. So you can go buy a laminate that's half ounce or 5 micron copper on both sides. The dielectric is only 13 microns thick and has a dielectric constant of 45. So it is not FR4. It is a rare earth mixed with a ceramic. And so it's extremely brittle. So you can't mess with it like normal FR4 because if you crack the ceramic, it's useless. Not a lot of people around the world know how to work with the kind of exotic materials you need for 5G and for super high frequency stuff. But you can go to my book that's free, or you can go to the PC handbook to look at who makes these materials and why they're used, et cetera, et cetera. But we're talking only about the HDI layers. The part right here, the center part can be FR4. You know, the core can be conventional multilayer. This whole day is really directed not at the core, but at those layers 1 through 3 and 1 through 4 that are on the surface. That's really all I'm talking about is what's happening on the surface, not what's happening in the center. And so here's the graph on plane capacitance and inductance as a function of dielectric thickness. And again, apologize for it being in mils and not millimeters. You know, normally my audience is North Americans, so, you know, it's not Europeans or Asians. But you notice the blue line there is capacitance, and the orange line is inductance. Well, look what happens to inductance as you head towards 0. Inductance goes to 0. So the thinner dielectric you can find is going to have an inductance of directly 0. Now, look what happens to capacitance as you get very thin. It goes up to infinity. So thinner is better. If you can work with these very, very thin materials, especially the power distribution network, you can eliminate the noise and the headaches that you're normally working with if you're using 75 micron or 100 micron dielectrics. The FR4, stop doing that. Go and at least work with 75 micron or 50 micron, or consider materials that have higher dielectric constants but that are very, very thin, because that thinness lowers the inductance and increases the capacitance. And so here's a list of those materials and the trade names of those materials, where you'll find them, and whether or not they're, and you notice the first 4 are called sequential lamination. That's because you have to etch a pattern on one side, laminate it, and then etch the pattern on the other side. You cannot etch both sides simultaneously. The material will crack and fall apart. So these are not FR4s. Almost none of these are FR4s. You just simply can't do it with an FR4 material. Farther down the line, you'll see some 50 micron and 75 micron. You can use those. They were lower cost, but also if you look at their inductance and capacitance, they're very low on the inductance and capacitance. The really, terrific materials are more exotic and more expensive. The second thing is how you use them. If you use them like this, where ground is here and power is over here, don't waste your money. You haven't accomplished anything. You got to get power and ground closer together, like this. But what's better than this, because notice you have inductance here and you have inductance here, is move the ground to the surface, so that's the only inductance you have in the current loop. You want that current loop as small, geometrically, and as low as inductance as possible to get that loop as small as possible. So why do we move ground to the surface? Well, it lowers our loop, lowers our inductance, provides EMI shielding, and there's fewer vias. There's a whole list of reasons why we changed the architecture different from the conventional multilayer. Do you have to do it? No. Do you want to have a job 10 years from now? You better learn how to do it and why you're doing it, because the way you're doing it now is not going to be good enough 10 years from now, I guarantee you. So sooner or later, you're going to have to learn some new stuff. And one of it is getting rid of a 40-year-old construction for multilayers that's simply no longer justified. too old and too inefficient to handle modern day circuitry. And 5G is the turning point. You're not going to make 5G boards work with the old rules. You're going to have to go to the new material and the new rules to accomplish the 5G. And 5G includes all the autonomous vehicles and the robotics and the smart factory and all these other things are all tied to that. So the distributed capacitance reduces power bus noise. So if you study this, I've got 5 different materials, including FR4. So this is the noise on this right here, this is FR4, the big ones. The littlest ones that you can hardly read right here, these are the exotic materials from 3M, Oak Mitsui, and DuPont. And they were prior listed. Why do you use those expensive materials? Because you need a very low powered supply impedance and you need to reduce noise on sensitive circuitry. And so it also looks like this. So this is the DuPont materials, and there's a frequency versus radiated field emission in dBs of these materials. These are in my book. Same with this one right here. This is noise on the power distribution network as a function of a 50 micron material, 25 micron material, and 18 micron material. And you can see the difference in noise as the distance between the power and ground shrinks, down to the smallest we have available is 18 microns between power and ground. Things like that. Another way is if you have an eye diagram. This is an eye diagram of the signals. This is not FR4, this is kind of product B, but these are the distributed capacitance material, up to this one right here. This is exactly the same signal. The only thing difference is the material between the power and ground in the construction. So material is very, very important, especially the new materials, and especially the HDI materials that cannot be used in a multilayer. So if you're designing only multilayer now, you're not going to encounter these materials because they're not suited for a conventional multilayer. They assume that you're going to laser drill and that it's going to be up near that surface. The core can be FR4, but and so if you put the critical nets up in the surface where the material is, then you've handled the most critical nets, and the rest of the nets can go in the conventional design strategy. So we have these high-speed constraints all over the place that are single-ended differential, things like that. So I work with a lot of signal integrity simulation. And fortunately now we have signal integrity tools that know the difference between a blind via and a through-hole via and a stubless mechanically drilled out via, so that we could actually simulate what the electrical performance of these circuits are going to be, which is what you're seeing here, especially when it comes to power integrity. And the power integrity is very important because as they shrink the pitch, and you're going to use a through hole, you've got to drill these great big, you got to have these big anti-pads around your signals, but the thing shrinks. And if it comes to the point where you've removed all the copper, then you don't have a return path. And all of a sudden you start getting a lot of noise because it has to meander around until it finally completes the circuit. And it will complete the circuit. Even if it has to meander all over your board and create all this noise, it will figure out a way to get back to its source. But it's invisible because although you route the signal going out, you depend on planes to get the signal back. But like I was telling somebody, remember, for a high frequency signal, the return path is the path of least inductance. For the power, it's the path of least resistance. Not the same. And many people are still thinking least resistance And no, that's not what you're dealing with. You're dealing with path of least inductance. What is the path of least inductance? Well, actually, if you have a signal going out, the path of least inductance on the plane is closest to the signal going out. And so, although you have this plane with all this copper, all of your return paths are sitting there following your signal going out, because that's the least inductance. All this other copper is doing you no good at all. Now, 40 years ago, that was different, because circuits were slow enough that resistance and inductance were essentially the same. But now, you've got power distribution and you've got signal, and signal return is inductance, not resistance. Power return is resistance. And it took a long time to get power integrity tools that could take into effect this geometric bias we have on electrical fields. And it took mostly Russians. Almost all this software is complement of the Russians. The Russian mathematicians solved the problems that Americans and Europeans couldn't figure out. I know because I was given the job of explaining to the Russian physicists that they need to write technical papers to explain to the Americans how they solved the problem, because the Americans said it was impossible. And the Russians kept telling me, no, this is a secret. I said, no. You're not working for the Russian military anymore. You're working for us. And we need you to explain how smart you are and how you solve the problem, because we got these Americans over here that says this is impossible. They're just simply ignorant. And so we need you to write it so that, that they don't realize that they are ignorant and need to learn something, that the Russian math is better than the American math. And it was such a long time to convince the Russians to write papers for the IEEE so we could explain why it does work when nobody else could understand how it worked. The Russians were that much smarter than we were. I mean, really much smarter than we were. But so we hired them. They worked for us. So, but they kept saying, but this is a secret. We said, no, it's not a secret. Not anymore. He said, you need to explain it, take credit for it, we'll give you a bonus, but you need to write it down, because these engineers and scientists over here don't understand it. And it finally worked out. We could give them a lot of money. They realized, capitalism, I like this, having money. And so it was a big challenge how to analyze vias. Vias are a real tough animal to do three-dimensional signal and power integrity to. Took a long time, but with the Russians' mathematicians' help, we finally got ways of breaking vias down into elements that could end up in signal integrity tools. And so in power integrity, this was a standard training board, and I redesigned it to a 12-layer HDI, but I built it in 4 different versions. So I had a 12-layer, I had a 10-layer, I had an 8-layer, and I had 2 8-layers. And what I did was I built it with different generations of HDI technology. So this is sequential lamination, all mechanically drilled. This is generation 1 HDI. This is a generation 2, and this is generation 3. So we'll talk about which generation of HDI. But you notice that what started out as 16 layers is only 8 layers over here. And you notice it's all stubless. And so we'll talk about generation 3 HDI that's 100% stubless, but nobody in Europe makes it. If you want this, you have to buy it from the Japanese or the Taiwanese. You can't buy it in North America, but you can buy it from the Taiwanese or the Japanese. And it's superior technology to anything we have in Europe or North America. Why people don't build it here, I don't know. Why we don't do it in North America, I don't know. But the technology is there, and we'll talk about it in the next hour. But anyway, so there are there are 5 different designs for the very same schematic and components. And they go from 18 layers to 8 layers. And they're enormously different in cost, but they are exactly the same PC board. Exactly the same. Which I like to emphasize to people, there's an infinite number of ways you can take a bill of materials and a schematic and design it into a PC board. There's an infinite number of ways. Give it to every one of you, and every one of you will do it different. There's no necessarily the best. It's just different. Every one of you is going to come up with a different design, I guarantee it. And probably they'll all work. Will they all cost the same? Well, that I don't know. Will they work equally as well in terms of noise? Well, don't know. It depends on how much expertise you have acquired in terms of solving these little problems that come up. So here's the original design, 16 layer. And this thing had a 1500 pin FPGA and a 940 pin BGA and a 496, 16-1 flash memories at 0.8 millimeter pitch, and it had 1.25, 2.5, and 3-point voltage rails in it. Here's the 12-layer HDI stack up kind of thing. And so, so here's the effect of reducing the plane separation. So this is a 1-inch by 1-inch PC board. And the power distribution between power and ground is 1.5 millimeter, and the other one is 0.75 millimeter. So if we only reduce the distance between power and ground, you can see the effect between blue and yellow of moving power and ground closer together. There's a shift in frequency and a lowering of some of the peaks. Now, if I move that 1.1 out to 10 by 10 inches, there's a more effect because now there's kind of more spreading going on. So this is a bigger board, but of the same construction. So the blue there is FR4. So instead of being FR4 material between power and ground, what if I use the oak Mitsui material that has a dielectric constant of 16? So this thing, everything's identical except the distance between power and ground. The blue is FR4, and the yellow is oak Mitsui that has a 4 times higher dielectric constant. So it doesn't have a dielectric constant of 3.8 or 4. It has a dielectric constant of 16. Why? Because they put tantalum nitride into the epoxy. And so they put a ferromagnetic material into the epoxy that's kind of a very high thing, and it moves the epoxy from 4.0 up to nearly 16. Now, today, universities are researching this. So universities have supplied to me dielectric constants of 35, 55, and 78. So some universities have a metamaterial that has a dielectric constant of barium tantalate, that between power and ground we have a dielectric constant of 78. Well, that's a fantastic capability to improve our high-speed multilayers with barium tantalate kind of thing. Here's the difference in placement of vias. So we have a decoupling capacitor, and what we chose is we have a via and pad for this capacitor. We have a via separated, and the via is even farther. So it's the very same capacitor. And then also, the capacitor is connected to power distribution on the surface, in the middle, or the far side of the PC board. So the effect of this right there is it moves from the blue to green to yellow. So as you move the vias closer together, the current loop gets smaller, and it shifts to a higher frequency kind of thing. So that's the effect of a 0.01 microfarad capacitor, where the mounting distance of the vias, just the distance, affects the electrical performance. This one right here is the yellow is where the power ground plane is adjacent to the component. The green is in the middle, and the blue is with power and ground is the far side. So now we have inductance to get to the power distribution and inductance to get back. And this is the effect that it shifts the frequency response in terms of how big that via is to connect to power and ground. And then the last thing is voltage drop. Okay, so the top one, this one right here is mechanically drilled holes for the BGA. These one are laser drilled holes. And you can see the difference in the voltage drop if you read the voltage. That there's an enormously higher voltage drop because we took away so much copper than when we use the laser down here. And that's an effect that most people don't realize or see, that as you go to finer and finer pitch and you use through holes, you have less and less copper, and the resistance becomes more profound. So the voltage actually drops at the BGA pin, which increases the noise problems within that because you've lost your voltage rail. So that was that list. You know, the voltage rail trade-off, that's somewhat invisible, but you can pay a lot of money to a signal integrity guru, and he will tell you, you know, to switch the size of your connections because you've taken away all the copper for the power distribution. And that's what I call right now the Swiss cheese. So this is a 0.8 millimeter pitch BGA. This is what the planes look like, the Swiss cheese. The one next to it right here is 0.8 millimeter, but these are the micro vias. And you can see the difference in copper because it's color-coded. This one right here is color-coded for voltage drop. And so that's not even fine pitch. You know, that's simply the difference between mechanically drilling a big hole and using a laser drilled small hole. You know, and so, and it's not just voltage drop. This is the impedance. Look what happens to the impedance. Over here, this one has the yellow line. This one up here is this blue line. The impedance drops if you don't remove all the copper. You know, and so what am I getting to? Miniaturization. Physics likes things small. It likes it thin and small and close together. That's simply the physics of fields. And that's what you're fighting, is that as rise time gets shorter and shorter, you're fighting the responsiveness of that field, of that switching levels. So you're fighting physics. You're not going to win. Physics is always going to win. You've got to learn how to adapt the fact that the changing electronic is making things tougher and tougher for you. I'm afraid nothing else I can say. It's just getting tougher and tougher to do your job because the semiconductor people are doing their job, and their job is making it harder for us to do our job. And the things that are killing you are the old ideas and the old ways that we've always done it this way. Yes, you've always done it that way, but unfortunately, you haven't always had these new chips, and the new chips require a different way to do it if you want to succeed. So I think as I had shown you like this, you know, covered before, we want 0.1 ohm power distribution impedance. The blue is the 0.8 mil C-ply. The yellow is the C-ply without the decoupling caps. Notice how much better it is if you take the decoupling caps away. So I advocate you use distributed capacitance, but remind you must remove the decoupling caps because the decoupling caps forms tank circuits that makes things worse, not better. So more capacitance is not better. Not if you're going to use planar capacitance. You must remove the decoupling caps. Otherwise, you're going to be in a world of hurt. And nobody's ever said that out loud. Everybody said, buy my material, but they never say, oh, by the way, you got to take away 80% of the decoupling caps if you want my material to work. I never hear the salesman say that, yeah, the material is great, but it's only great if you get rid of decoupling caps. The two together are not better. The decoupling caps make resonant circuits. And the special material in yellow is better than FR4. FR4 is the blue, yellow is the C-ply material. And if you're going to use FR4, then thinner FR4 is better than thick FR4 down here, which is yellow versus thick. So there are several sets of rules depending on what you want to pay and what you want to use, how you put this all together. And then, like I said, like on the example, the 3.3 volt supply, the final design had 80% fewer decoupling caps than the original design. And so if we want this thing to work, you can't go to zero. You can't take away all the decoupling caps. But you have to get down to only 10% or 15%. But if you do not do it, you wasted your money on the material, because the decoupling caps defeats the advantage of the material. You got to rethink the whole thing. The good news is that it's a lot easier to design a board with 80% fewer decoupling caps right in critical areas that you need for something else. Now the decoupling cap doesn't have to be there. It has to be over here on the board, but it doesn't have to be right there where everything is crowded together. And the same is true for the 2.5 volt supply. Oh, good. And that brings us to the end of this session. If you download my HDI handbook, the signal integrity electrical performance chapter was written by Dr. Bogentin, not by me. And Eric agreed to write the chapter for my handbook on HDI because he's the expert, I'm not. So if you happen to look at chapter 3 on signal integrity and electrical performance for HDI, it's by Dr. Eric Bogentin, not by Happy Holden. And believe me, whatever Eric says is the gospel truth, even if you've never heard it before or seen it in any textbook. It's the way it really is. So several other chapters are written by other people that I consider more expertise than I have. And the whole thing isn't written by me. It's written by other experts, people that I believe know more than I do, that need the benefit of their expertise, not just mine.